So let's go ahead and get started. First thing I want to do is apologize. There is no prep activity 1 right now on the lab. That is a placeholder I put in this summer to remind me to make a prep activity 1. And then I forgot about it till this week when you all started asking what's with prep activity 1. So I will do that sometime in the next week, but you won't be responsible for it. It'll be for like future classes. So all you have to worry about is prep activity 2. And we also have our homework quiz today, which is I think where most of the questions are coming from today.
Yeah.
So what questions do we have?
Can you do number 1A?
Sure. What is 1A?
It says how many moles of X are present in each solution. So there's 100 milliliters of 0.125 molar NaOH, and X is Na plus.
100 milliliters of
0.125 molar NaOH.
So the first 4 problems of the homework are supposed to be review problems from the first 2 weeks of class, back when we first started learning about units and conversions. So what we want to do is we just want to remember some of our conversions. 100 milliliters, what does molarity mean? So I'm going to go ahead, I'm going to convert my 100 milliliters to 0.1 liters. I'm going to multiply by 0.125 moles per liter. That's going to give me moles. And I should be specific, this is moles of NaOH per liter, right? Whenever we say moles, that's just a counting number. We need to be specific. I can do this math in my head. 0.0125 moles NaOH. The other thing we have to realize is how many sodiums for every sodium hydroxide? 1. So I can go ahead, if I want to be most mathematically correct, I can go ahead and say I've got 1 mole Na for 1 mole NaOH. That would be Na plus. So notice this cancels out. It's a 1-to-1 ratio mathematically. That's really boring. That just gives me 0.125 moles Na plus. But chemically, that's really important because this ratio, this ratio allows me to change what I'm talking about from the molecule, from the ionic compound, to the individual ions. What if I wanted to know how many moles of hydroxide were in solution?
Do the same thing.
Same thing, because it's also a 1-to-1 mole ratio.
So for BaCl2, for example, it would be, if they're trying to find the number of chlorine atoms, and you get 0.001875 moles.
So let's go ahead and do that problem. What does it have for, what does the problem give you for doing that?
Oh, it says 1.25 liters of 1.5 millimolar.
Little m?
Yeah.
Okay.
And then barium chloride.
Okay. So we do the same thing. We're going to do 1.25 times 1.5 times 10 to the minus 3. That takes care of the milli. Oh yeah, don't forget the times 10 to the minus 3. That is going to give us, if I could do math in my head, something like 1.75, 1.8. Am I even close?
Oh, I already multiplied by the molar already, so I don't know.
So you multiply these two together.
I need it. 0.001875.
0.001875.
Yeah.
Or we could call that 1.8 times 10 to the minus 3, which is about what I thought it should be. But I won't trust math in my head. And this is moles BaCl2. Then if we say, okay, we want to know moles of chlorine ions, I need to know how many chlorine ions for every barium chloride.
2.
So you just do 2 moles Cl minus for 1 mole BaCl2. You can cross So you just double it. You're gonna have 37 something, 0.0037 something. If I could do math in my head.
Yeah, 0.00375.
003. Really, 375?
Yep.
Cool. Okay.
What? That doesn't make sense.
Why doesn't that make sense?
Because it shouldn't end with 5.
Oh yeah. Did you round?
No, I just put in times 2. 0.0. 0.00187.
Oh, he's right.
No,
Okay.
It ends with it's a placeholder. It's like
Yeah. So it's 3750.
Yeah.
Right. That's what you're thinking of because of the 5 rules. Multiplication.
Good thing.
Cool. So, and then that's how all of those problems should work. The first 4 are all kind of getting at concepts like this that we've seen in the past, but maybe far enough in the past that we don't quite remember them.
Did you do?
I did 4. I only got to the grams part, and I just forgot how to put it into moles.
Which was number 4?
The molarity of a solution prepared by placing 13.8 grams of potassium carbonate into 500 milliliters.
So, and you're like, how do we get between grams and moles?
Yeah.
So what's the unit? Let's go ahead and do that one real quick. It's good reminders. So, how many grams are we putting in?
13.
13.8 grams of
Potassium carbonate.
K2CO3.
Yes.
So we want to get to something, and we want to get to somehow. We want to get to moles K2CO3 per a liter. So we're already given a volume, right? What's the volume we're given?
500 milliliters, so 0.05 liters. Or 0.5 liters.
So really the only thing we need to do is we need to convert this grams of K2CO3 into moles of K2CO3. The thing that gets us between grams and moles?
The atomic weight of
Yeah. So what we're going to do in this case is we're going to do, we have to get the,
Molecular weight.
yeah, we have to get the molecular weight. We have to get the molecular weight of K2CO3. That will make it so we can do 13.8 times 1 mole K2CO3 for some number of grams.
138.41.
138.41.
I think.
I believe it.
That's close to
Right. If we round it to 138, the answer would be 0.1. So it's going to be approximately 0.1 moles K2CO3. And then I can just do molarity is going to be 0.1 moles divided by 0.5 liters. And if I can do math in my head correctly, that's 1/5, which is 0.2 molarity. Notice as well, this is another idea that we talked about back when we did the absorption lab. When I'm talking about molarity, I'm only talking about the molarity of a particular component in solution. Right? So this molarity is the molarity of potassium carbonate in solution.
Right.
It's not the molarity of anything else in solution.
Got it. I'm good.
So if you had 2 different compounds in the solution, would you have to find the molarity of each individual?
Yes, you'd have a molarity for each compound in solution. Just like, you know, because this is a kind of stuff per liter, right?
Yeah.
You wouldn't be like, oh, well, there's just, everything's pretty much the same. You'd need to count one type of atom or molecule and then the other type of atom or molecule. You'd count those separately.
Okay.
And then number 5, I had a question on.
Yeah, which one's number 5?
It's the combustion of propane, C3H8, and O2.
Uh-huh.
And so I just wrote C3H8 gas plus 5 O2 yields 3 carbon dioxide plus 4 H2O.
3 CO2s
Yes.
plus 4 H2Os.
Uh-huh.
Okay.
And then is that considered a redox reaction?
Yeah. How can we tell it's a redox reaction? So you'll notice you've got 3 carbons, you got 8 hydrogens, you've got 6, 7, 8, 9, 10 oxygens, this is all balanced. We say, how can we tell that this is a redox reaction?
So something's oxidizing or gaining.
And how do we tell whether something's oxidizing or gaining or reducing and losing?
Say 2 oxygens in the final product.
Yeah, and you notice the charge on this oxygen is going to be 0. The charge over here is going to be -2, and the charge over here is going to be -2. So clearly my oxygen is changing charge. My oxygen is gaining electrons, so my oxygen is going to be reduced, which makes sense because oxygen oxidizes things. It's the oxidizing agent. It gets reduced, but the other thing gets oxidized. So that means the C3H8 must be oxidized. And we can kind of do a weird thing. The carbon here must be in a +4. And then I want to know the average charge on the carbons here. Right? So, and this is a weird thing. We didn't get into this method. I would have gone into this method for finding oxidation states if a lot of you were going on to organic chemistry, but since most of you are not, I decided to skip it. And so we can just look at this in terms of the average charge. So I'm going to say each hydrogen is a +1, and I've got 8 of those, and then I need that to be distributed over the 3 carbons. So that means each carbon needs to be, what is that? 2.3 charge? No, 2.6 charge. If I can do math in my head again. 2.67. And it's going to have to be the negative charge. So the average charge on the carbon is 2.67 negative. And if I do 3 times 2.67 negative, I should get 8. And that's going to balance out the charge. Now, of course, we don't have the, well, we probably actually do have these partial charges, right? The idea that each carbon has a charge goes back to that idea that electrons are static things that aren't dynamic, that aren't moving. But the way that we typically do oxidation states for organic compounds is we look at the Lewis structure. And we can tell based on how many hydrogens are next to it what the charge on each one is. The fact that this has 2 hydrogens next to it means this one's probably a -2. The fact that this one has 3 hydrogens next to it means this one's probably a -3. The fact that this has 3 hydrogens next to it, this one's probably a -3. 3, 6, 8 charge, that's going to balance it. But again, we only need to understand that we can just look at the kind of average charge because these charges are going to be distributed over the entire molecule.
Got it.
But this is definitely a +4, so we can tell that carbon is losing electrons. Which means it's oxidized. Oxygen is gaining electrons, which means it's reduced. Okay. We also could figure that out without actually calculating the oxidation states on those carbons. We could figure that out just by the fact that there's oxygen here, which is an oxidizing agent, which means the other thing has to be reduced. One of the common mistakes people make is they look at this and say, oh, it's an acid-base reaction. Water's a product, and this has hydrogens.
Yeah.
That's not actually correct. None of these hydrogens, remember, in order to have acidic behavior, we need the hydrogens to be slightly polarized. That is to say, we need an electronegative group next to them so that oxygen-hydrogen bond, typically the oxygen-hydrogen bond, can be broken by the IMFs of water. That dissociation can occur. In this case, these are very close to each other in electronegativity. So in all actuality, this is not going to behave like an acid. Plus, it's a gas.
Yeah.
Right? We're doing a gas-gas reaction, which reminds me, my chemical reaction is wrong. Always have to have states of matter in order to be correct. And the H2O we produce, I believe, is a gas in that case as well.
Yeah. And minus is combustion, so it couldn't really be a acid-base reaction.
Right, right. Combustion is always a specialized version of redox. It is essentially, it is a redox reaction. It's just, there's a lot of redox. There's a lot of combustion reactions.
So when you combust, like let's say like gasoline,
Mhm.
why does it not just produce CO2 and H2? Why does it produce,
Good
like,
question.
other things?
This is kind of what we saw in the thermite demo yesterday, right?
Mhm.
Where thermite should have produced a really nice, like, should have just produced iron and aluminum oxide. There's nothing that suggests smoke should be produced. There's nothing that suggests any gaseous products should be made. But the reaction isn't perfect, right? So the big problem with combustion is this assumes complete combustion with the correct stoichiometric ratio. So you know cars. So if you have a good enough carburetor, this will happen, right? Because you get the right mix of fuel to oxygen.
Right.
But if you don't have the correct mix of fuel to oxygen, you're going to have side products like carbon monoxide. The fact that the air you're burning with also has nitrogen, you're going to produce nitrogen dioxide and nitrogen monoxide because there's a lot of nitrogen in the air that we're pumping into the engine. Unless you got an oxygen tank that's pumping pure oxygen into your fuel mixture, you're going to have all these side reactions. Then the fuel itself is not actually pure. There's sulfur compounds, there's nitrogen compounds. The sulfur compounds in fuels where you get sulfur dioxide and sulfur trioxide as a byproduct of the fuel. And that byproduct is what was originally what was creating really bad acid rain. This was 80s, 90s, it was a huge issue. They changed the refining process, they made the regulations more strict. They aren't allowed to have as much sulfur side material in the fuel now. And then the nitrogen is what produces nitrogen dioxide or dinitrogen tetraoxide, which is what makes the sky brown. That's smog. Carbon monoxide, which happens when you don't have enough oxygen in your fuel mixture. That is why we have catalytic converters. So carbon monoxide is very toxic. Remember, we looked at the structure of this and we were like, "Ooh, that looks weird. That's the carbon triple bonded oxygen." And we're like, "Yeah, that doesn't look like any of the typical pieces we see. Very reactive, very dangerous for like inhalation risk." Carbon monoxide poisoning is something that kills people in their sleep. So catalytic converters essentially trap this and then react it with excess oxygen in the air to make carbon dioxide. Now you might look at this and think with today's current environmental climate concerns, you're like, whoa, carbon dioxide is not good either. But relative to carbon monoxide, we're talking immediate poison versus long-term environmental poison.
Right.
So still a step in the right direction.
Yeah.
Now if we could just trying to think of what you could do to carbon dioxide to break it down into something else. If we just take all that carbon dioxide and have some sort of filtration system that could turn it into like sugar and produce oxygen as a byproduct, that'd be great.
Yeah.
And that's trees.
Right?
Nature already did that.
Could you separate it into like solid carbon and gaseous oxygen? Would that be pretty
Theoretically, we could write that down on paper, right? But when you look at carbon dioxide, you got those carbon-oxygen double bonds, and that's going to be a huge energetic cost. Like when you look at trees and plants and leaves, those are very specialized systems that have very unusual like enzymes and mechanisms specifically for trying to break down carbon dioxide, turn it into cellulose, sugars, and oxygen gas.
So this is just all perfect, kind of like in a perfect
exactly.
world, so.
This is all I'm reacting is this amount of propane with this amount of oxygen. I've got the correct stoichiometric ratio. Everything's going to go great.
Okay, got it.
Nothing else is going on. In the natural world, that's not the case.
Sounds good.
Other questions? 9?
Can we do like all of number 9?
Oh my goodness. We can do a couple of number
Okay.
9. Do you have a few that you'd like to do from number 9? If I remember correctly, number 9 is like A through M.
A through J.
A through J. See, not as bad as I thought.
So then we do all of it. No, I'm kidding.
Yeah, exactly.
Well, you can do all of it.
Oh, I can't. I tried.
Let's pick a few.
One is one from the beginning, one from the middle, one from the end.
Yeah, let's
A,
just
F,
pick.
A, F, and J. So let's start with A.
Wait, can we do B instead
Oh,
of A?
okay.
Sorry.
Let's do B.
I did
B,
A.
F, and J. Let's
Yep.
see how it goes.
Okay. So B is after lithium hydroxide is produced, it is reacted with exhaled carbon dioxide gas in order to remove it from the air supply. In this reaction, solid lithium bicarbonate is produced.
So B is a continuation from A. So like that after lithium hydroxide.
Okay.
Forget the after part,
Okay.
right? It's like the first reaction A is how we produce lithium hydroxide, and then we're going to further react the lithium hydroxide.
All right.
So let's just start translating words into chemical compounds.
So
Lithium hydroxide.
Lithium OH.
Do I need any charges or anything on this lithium? Right, lithium's a +1, hydroxide is a -1. And then if I remember correctly, this is a solid that's produced, right?
Lithium
Okay.
micro.
Yep.
So we're looking at lithium hydroxide. We're reacting it with,
Carbon dioxide gas.
which is,
CO2.
so I'm going to go ahead and write lithium hydroxide plus CO2 gas. And then the sentence says, will produce. So I'm going to go ahead and put my arrow to the product side.
Solid lithium bicarbonate.
Ooh, do we remember what bicarbonate is?
LiH carbonate.
Solid. And
I don't know what.
does it produce anything else?
Nope. It just says
Okay.
Is that all we have to do?
Then we have to balance
I
the
just
reaction.
saw the labels.
We
I
have
can do
to
that, but-
balance the reaction.
Yeah.
So I've got 1, 2, 3. Oh, this one's already balanced. 1 lithium, 1 lithium, 1, 2, 3 oxygens, 3 oxygens, 1 carbon, 1 carbon, 1 hydrogen, 1 hydrogen. So this, and then we can also talk about what kind of reaction this is. In terms of putting things together, we would call this a combination reaction. Right, because I'm taking two things, I'm combining them into one thing. You might also call it a synthesis, because you're taking two things, making one thing. Synthesis is usually a little bit more broad than that. Those are just talking about how the rearrangement is occurring. If we look at this in terms of a chemical reaction, it's not quite a precipitation reaction, right?
because it's solid to solid.
Because it's solid to solid. And if I look at this, I don't think it's a redox reaction. My lithium's +1, my lithium's +1, my hydrogen's +1, my hydrogen's +1. Oxygen's -2, -2, -2. Carbon in this case, let's check something real quick. +4. Carbon over here, that's -6, 5, 4. Carbon's +4. It's not a redox reaction. It's not a precipitation reaction. It turns out, and this would be tricky, the prompt doesn't even ask us to do this, but it turns out that this is a weird acid-base reaction. Right, where essentially the way that the CO2 and the lithium hydroxide are interacting with each other, this would be a weird acid-base type reaction. It wouldn't fit with the definitions of acids and bases that we did in class because we were only looking at strong acids and strong bases. This is something that I would give to my 129 students who spent the last 4 weeks studying acids and bases, and then ask them to try and describe how is this an acid-base reaction. And they would have to talk about electron donors and electron acceptors in order to get it correct. So it would be pretty tricky to get this as an acid-base reaction, but I'm pretty sure it's an acid-base reaction. You got the lone pairs on the carbon dioxide donating to the oxygen in the lithium hydroxide, so you have an electron donor, electron acceptor situation. Or is this going to no, the hydroxide is going to be the donor, the carbon is going to be the acceptor. And we could show that by actually drawing the Lewis structure for each thing and thinking about where the electrons are, where they're going. That's getting into organic chemistry style things. Just on the desk would be great. Perfect. And that's where you do electron arrow pushing diagrams in order to explain why different reactions occur. So that was B.
Yep.
We said we're going to do F as well.
Yep. So this one is when wine spoils, the reaction between the ethanol in wine and the oxygen gas in the air to form acetic acid and water.
Ooh, just inhaled water the wrong way. So, what would we write down?
C2H5OH.
Yeah, we could do C2H5OH. O2. Oh no, it's the ethanol, right?
Yeah, ethanol.
Ethanol.
And then oxygen gas. O2.
Gas. Yeah,
Yes.
you agree?
Yeah. To form
I'm
vinegar.
asking.
Oh.
You agree?
O2?
Yeah.
Yeah.
Okay.
What?
No, I'm just making sure because you were the one who had this question. I wanted to make sure
Yeah.
that we're not like just jumping past where you are. So then this is going to in my looks like a 10. Let's get rid of that. And we're going to go to produce. What do we produce?
Acetic acid.
Acetic acid. What's the formula for acetic acid?
C2H3O2 with the H somewhere in front of that.
Yeah, there's a couple different ways we can write it. The way I like to write it is CH3COOH. You can also write it as C2H4O2. You can also write it as C2H3O2H. This kind of separates the hydrogen off as like, oh look, there's next to these oxygens, you're gonna have this hydrogen that's gonna be acidic. This one is the simple molecular formula. This one's most suggestive. COOH is almost always trying to communicate that carboxylic acid group.
But all three of those work.
All three of those work. I find I prefer this one. This one is the most kind of simple. This one I think is better.
Could you have that H out in front? Like the first one, like H, C, like
You could, but remember we're trying to do a representation of the molecule.
yeah.
So we want that hydrogen to be close to the oxygens
Okay.
because that's where that acidic behavior is going to come from. Is the is the hydrogen next to the oxygen?
Yes.
That electronegativity of the oxygens is what makes it so this is going to have acidic behavior.
Okay.
And this is going to be aqueous. Oh, and also was the ethanol liquid or aqueous?
It just says ethanol and wine, so I'm gonna guess that it is aqueous.
Yeah. Why are we going to say aqueous in this case?
Because wine is a solution.
Yeah. Right. Wine is a solution. It's mostly water actually. There's just a little bit of ethanol, a little bit of sugars, a little bit of like trace minerals and other chemical compounds that gives the smell and flavor. We have the acetic acid produced, and what else do we produce?
Water.
What kind of reaction is this? So, first things first, is it balanced?
No.
No.
Wait, just kidding.
Yeah.
Sorry, I didn't see the water.
No.
3, let's count. 2 carbons, 2 carbons. 1, 2, 3 oxygens. 1, 2, 3 oxygens. 5, 6 hydrogens. 3, 4, 5, 6 hydrogens. It's actually already balanced. We're picking some easy ones to do. Nice randomization. So this is again a reaction that's just a 1-to-1-to-1 ratio, right? It's all balanced already. Now we can go ahead and go beyond the problem if we wanted to and say, okay, what type of reaction is this? First off, we can tell, we'll write down all 3 types and just do some elimination. Is it a precipitation reaction? No. Definitely not. Okay, so now we're down to a 50-50. Acid, base, or redox. If we look at this, we might think, okay, water's a product, and I've got an OH here. Is that going to be like acidic, basic?
Because acid to acid, so.
Well, maybe oxygen. Oh yeah, acid. There's an acid in the product. You're right.
So you can't go acid basic because there's no real.
Yeah. So doesn't look like it's going to be acid base. So then it must be redox, and we can also tell it's redox O2 in a reactant, and then no O2 in the products. So this O2 is clearly going to go from a charge of 0 to a charge of -2. So that must be a redox reaction. And then the carbons, again, are going to change their charge like they did before. Oh, different problem. And we can, again, go with the average charge on the carbons rather than doing the Lewis structure oxidation state charge. And let's do the last one.
Okay, so J. Ammonium nitrate.
Okay, so let's think about this while it's being read.
Ammonium nitrate decomposes explosively to form nitrogen, oxygen, and water vapor.
Okay. So, this is NH4. Ammonium nitrate is NO3. No, it's not ammonia nitrate, it's ammonium. So this is the NH4 with the plus on it. This is the NO3 with the minus on it. That's going to be charge balanced. This is ammonium nitrate solid. Is going to go to, what does it produce?
Nitrogen, oxygen, and water vapor.
Water vapor is going to be gas, oxygen is gas, nitrogen is gas. This one, finally, we need to do some balancing. Wait, do we? Yes, we do. Okay. So, notice I need 2 nitrogens. Oh no, I've got 2 nitrogens. 4 hydrogens. Oh, I don't have enough hydrogens. Okay.
Didn't you say earlier in class that anything that had a nitrate would be aqueous?
If we put it in water.
Oh, okay.
Right?
Yeah.
So you can think about it like all sodium compounds are aqueous, but only if they're in water. Like we can have sodium chloride out on the table.
Yeah. Okay.
Same idea, right?
Okay, yeah.
So let's go ahead. Let's start thinking about how we balance this equation. I should have given myself more space. So we're gonna have N2, O2, H2O, gas, gas, gas. Okay, now when I look at this, I say, okay, I've got 4 hydrogens. I've only got 2. So I'm going to have to double this, and that's going to throw off everything else. I've got 2 nitrogens, I've got 3 oxygens, I've got 4 oxygens. Oh, what a headache. So now I have to start thinking about how I can double things. Now, clearly the biggest problem in this balancing is going to be the NH4NO3 to the H2O. And if I have an even number here, I want an even number there. So if I put a 2 here, then I'll want to put, that's going to give me 6 oxygens. And, sorry, that's going to give me 8 oxygens. I'm gonna put 6 oxygens, 4 hydrogens. If I put a 4 there, that's going to be 4, 5, 6 oxygens. That's looking good. So that takes care of my hydrogens and my oxygens.
And then you see the 2.
And then I just need to have 1, 2, 3, 4 nitrogens. 4 nitrogens. That should take care of it. And from all of this, can we tell without thinking too much, can we tell what kind of reaction this is? It's a redox reaction, right? We're going from oxygen with a charge to oxygen gas. Now this is kind of the opposite of a redox, of what we've seen in our typical redox reactions, right? This is something that's essentially decomposing itself in a redox reaction. Ammonia nitrate is an explosive. It burns. It produces its own oxygen to help it burn. But the difference between things that like burn as fire and things that explode is the concussive shock wave made from a bunch of gas production. A very rapid reaction that produces a lot of gas is going to have this big shock wave as the gas expands.
So why did it produce CO2?
Are there any carbons for it to react with?
No. So not all combustion creates CO2.
Right, and notice we didn't technically call this one a combustion, right?
Oh, it's cool.
Yeah.
Because it's not reacting. It's not reacting with an oxygen. It has
Right.
the oxygen inside of it, and that compound is just breaking apart.
Yeah,
Not
so
as-
normally when we talk about combustion, we're talking about a reaction of some fuel source, and it can be any fuel source, reacting with oxygen.
Oh,
And
not
normally-
with cell,
Normally our fuel source is something like hydrocarbons, methane, ethane, propane, octane, stuff like that. There's a whole category of explosives that are not combustion reactions. They're still redox reactions, but they're not combustion reactions in a typical way. Another really common one to look at is, let's see if I can remember it. I can't remember it right now. I think it's ammonium perchlorate, NH4ClO4, and that's rocket fuel. The reason that ammonium perchlorate and even ammonium nitrate would work as kind of like fuel for rockets is if you're in space, you don't have any oxygen to burn, right? You're in a vacuum. So you need a solid that's going to decompose to create the oxygen that you can then burn. Or they just use these sometimes to produce just a burst of gas to like push it. And so things that are somewhat stable and lightweight. And the reason they use ammonium perchlorate, if I'm remembering that it's ammonium perchlorate correctly, the reason you use ammonium perchlorate instead of ammonium nitrate is just gas per mass, right? You want to get the biggest amount of energy out of the lightest weight possible thing, because every gram you're sending into space is expensive. So, do you think you can do more of those?
I can do all of them except for H and I,
Oh,
but I should probably figure it out.
what's H say? Can you get the formula or is it the balancing?
It's not the balancing I can do.
Okay.
It's the phase labels.
Oh, the phase labels. Let's go ahead, let's read through H and see if we can get it.
The main ingredient in household bleach, sodium hypochlorite, is formed by a reaction of sodium hydroxide with chlorine gas. Sodium chloride and water are also formed.
So, we're going to do sodium chloride, which is NaCl, with, wait, was it?
No, sodium hydroxide and chlorine
Sodium
gas.
hydroxide, sorry, sodium hydroxide, NaOH plus Cl2. Now it says it's gas, we're going to do Cl2 gas. The NaOH is not mentioning anything about solutions,
No.
so we're going to go with solid NaOH. And then on the product side, we've got sodium hypochlorite, which is NaClO,
Sodium chloride
NaCl,
and water.
H2O.
So now if you have water, would you say that that sodium chloride is aqueous?
Ooh, good question. So, it really depends. Like, so here's a funny thing. Let's say I've got a block of salt. And it's a big block of salt. And I put a drop of water on it. Would you say the salt is aqueous?
No.
Right. And you kind of say, well, maybe like right where the drop of water hit it, there's some aqueous component there. But if I wanted to most represent what's happening in reality, I'd still call it solid.
Okay.
Right, so my guess is that the amount of water you're going to produce in this case, first off, does it say whether it's liquid water or
Just what it says in household bleach. So it's it's the main ingredient in household bleach.
right,
But we don't know if the water has been added yet to household
Right.
bleach to make it an aqueous solution.
yeah,
So it just says that sodium hypochlorite, sodium chloride, and water are formed.
okay.
It's not specific on
The phase of the
phase
water.
the phase of the water.
So there's some ambiguity there, which is less than ideal.
Mhm.
Probably going to be liquid water.
Yeah.
But in that case, if you put liquid water or gas water, you would get credit because it's ambiguous.
Okay. Same with the hypochlorite and sodium chloride. If you put, or would you want those both to be solid?
Sodium hypochlorite, probably a solid, and sodium
Okay.
chloride, probably a solid.
Okay.
right? So the reason I'm like, oh, the water could be liquid or gas is because it's probably liquid. So in order for it to be a gas, you have to look at the energy of the reaction. Usually water vapor is produced when you're in a high energy reaction, so there's enough thermal energy to volatilize the water as well. Or if you're doing gas phase reactions, the water you produce is also gas phase.
Well, so then that is chlorine gas in the beginning.
Right, but the oxygens and hydrogens that it's reacting with are already in the solid phase, which is why I'm leaning towards liquid. Because is there enough energy for chlorine gas? Like, if it was reacting with oxygen gas or hydrogen gas, I'd be like, oh, it's already in the gas. Like, the oxygens and hydrogens are already in the gas phase, so there's some likelihood that water could be also in the gas phase.
But
Again, in any of these ambiguous cases, I give credit for either answer.
Okay. So if it doesn't specify how much or what phase it's in, just try and logic your way around what you think it could possibly be.
Yeah, and that's the main thing I've been trying to get everybody to do all quarter is like, forget the math, forget all like, the equations, and really just understand like the energetic drive behind everything.
So in letter I, the thermite reaction used in welding is a reaction for aluminum metal and iron dioxide to produce aluminum oxide and iron metal. And I wrote it out. And so everything will be solid except, so would Al2O3 be solid as well? It would? Okay.
Yeah. It's a solid to solid solid. What type of reaction is that?
Redox.
Yeah. What information is missing in that chemical equation you wrote down? Yeah.
The gas that was produced with the oxygens.
The gas
That's
is probably a side reaction. That could be the potassium what was it? The potassium permanganate,
Oh yeah.
KMnO4, that was reacting. It could have been extra glucose that I poured in that was reacting. It could be just enough heat with things in the air reacting, because there's pollen and dust and stuff like that. It could have actually been reacting with the clay on the side, right? Because we also had it in a clay pot. The container got burned,
Right. So
it could have been reacting with the ceramic. The heat, like, so side reactions aren't represented. But the things I was looking for was the energy release was not represented, and the rate of reaction was not represented, right? In all these reactions we write down, we're not saying whether they're fast or slow.
Right.
We're just like, yeah, they exist.
Eventually they will happen.
Yeah, but like, just for example,
Damn double arrows.
well, they should all be double arrows.
Yeah.
We're just not there yet. It goes to Fe2O3. We balance that with a 3, 2, 4.
Do you have to put? No, you don't have to. You don't have to put the iron, the 2 on there, or.
But here,
Yeah, you don't need to put that.
the oxygen levels,
Oxygen
right?
tells, yeah. When do you put that again?
In the name. So if I was going to say iron
Oh.
2 oxide or iron 3 oxide, this would
Okay.
be iron 3 oxide.
Okay. But when you write out the formula for it, you don't need to because the charge of the oxygen tells you. Okay.
So this is the equation you were just looking at. Does iron rust?
Yeah.
Does thermite reaction happen?
Mm-hmm.
Do they happen at the same rate?
No.
No. If things rusted as fast as a thermite reaction, the world would be a very different place. Right? So that's something that's missing. Like, both of these reactions happen. Both of them are spontaneous. One takes some activation energy to get started. The iron oxide reaction, there's things that we can do to assist in this reaction happening, the formation of rust. Having salt water present to move charge around helps. having damp conditions, having hot conditions, all of those things help speed up the rusting process.
That's why you don't want to get iron wet.
Yeah, that's why.
And like boats are they always rust really fast because they have metals and.
Which is why a lot of boats use like brass railings and things like that. It's more expensive but less prone to the rust. So
Your cost in the future will be less.
yeah, so short-term versus long-term costs vary. I mean, really, if you wanted something that was not going to decompose like at all, gold is a really stable, or platinum. Both of those things are very corrosion resistant.
Super
Yeah. The cost benefit analysis might not quite be the same.
Yeah, that's an econ.
And your boat will definitely get stolen.
Yeah.
But we can are any of you gonna take 125?
Yeah.
Awesome, all of you are gonna take 125. So when you take 125, you're actually going to look at the energetics associated with all of these reactions, how much energy is released, and you can actually look at the energetics associated with the redox reaction, and just from the energy of gold gaining electrons, you can show why gold is more resistant to oxidation than other precious metals. Like if you look at gold, silver, and copper, you'll see that the reduction potential for each is different. Copper is lower. That's why a lot of things that have copper metal, you get that green patina on copper. That's from copper oxide. That's from just the redox reaction of copper with oxygen, and it has to do with the energy associated with oxygen stealing, essentially taking electrons from copper and forming that copper oxide. Silver does tarnish much slower than copper does, and it has to happen in the right conditions. Warmer conditions will cause that reaction to happen a bit more. But it happens less. It takes a higher, because the reduction potential of silver is different than that of copper. And then when you look at gold and platinum's reduction potentials are such that they don't even really react with oxygen. So that's why gold, I have a theory that part of the reason that gold jewelry was so cherished in the past and why gold became such like a big thing is essentially really twofold. One, it was, well, threefold. One, it was easy to mine because it's not very reactive. You can find it in pretty big chunks. Like if you want to do iron and steel and all of those things, you usually have to refine them. So those like became popular later. Two, it's a very malleable, very workable metal. Like you can pretty much, like, you can get a chunk of metal. If you have a big chunk of metal that's actually just gold, you can like almost just like massaging it with your hand change its shape. Most of the gold we use is like 14 karat, 24 karat. It's gold that's mixed with other things to give it better hardness.
Right.
But in like the past, they would essentially create alloys just by like rock pounding gold with other metals.
Right.
But it was a very workable metal, so you could get really fine detail and very elaborate jewelry pieces with it. And the third thing is it doesn't tarnish. So if you create a gold like piece of jewelry or a gold like staff that's passed on from king to king, like it looks the same. It looks like the same level of shines for like generations. It just doesn't tarnish the same as silver or copper. Yeah. So, but I've like, it's just one of those things I've always like. I really love the crossover of chemistry and history, and you know, it's always like you just gotta wonder, like, why is gold like the thing that everyone goes crazy over? Like, why is gold like, oh, we want the gold?
Yeah.
It's like, how did that become like the standard for all monetary transactions?
Yeah.
And so, like, if you look at the properties of gold, you're like, actually, yeah, it totally makes sense.
Yeah.
Okay. So I did two. So
Yeah.
three, you just.
It's the same thing essentially.
Okay.
I think.
And then I had one more question on
Sure.
number 7. I had on B and E.
What was number 7? Let's take a
7
look
was
at
the
that.
net ionic equations.
Okay. So, is there one that is emblematic of the other? Like, if we did one, would it take care of both? Or are they both pretty different?
pretty similar.
Which one do you want to do, B or E?
I'll do E.
Okay.
So HC2, H3O2.
Hang on a second. I picked up a dime pen. You said
HC2,
HC2?
H3O2. aqueous.
H3O.
Yeah, it's written weird. So
Huh.
it's just C2H4O2.
I'm going to put my H over there.
Okay.
Some of these problems I took from different textbooks, websites, other
Okay.
places,
Mhm.
the workbook, and not everybody agrees with me about the way to write things. So now that I wrote it this way, I can see that this is acetic acid,
Yeah,
right? So we've got acetic acid. I'm assuming that this is aqueous.
correct. Yep. And then plus NaOH aqueous yields NaC2H3O2 aqueous plus H2O liquid.
Okay. So we're going to look at an aqueous compound. We're going to decide whether we break it up or not. Acids. Yeah, so we're going to actually break that OH bond. We're going to have C2H3O2 minus aqueous. But, oh, before we do that, is the reaction balanced? It's best if we balance when we're in our chemical reaction before we go to the ionics.
No.
I got my C2H3O2, I got my C2H3O2, I've got my H, I've got my Na, I've got my Na, I've got my OHH, I've got my H2O. Actually, it is balanced. But always good to check, especially before we go to net ionic. Yeah?
For acetic acid, why do you always write the anion first?
So that is debatable whether that's best or not, right? So that's where on this paper it actually had the H out front,
Yes.
and the cation should actually be out front. I make a special exception for some of the organic acids because I want that hydrogen. Again, it's just about representation, right? I want that hydrogen to be next to the oxygens because those oxygens and that electronegativity is what's going to make it so that hydrogen can be acidic. So it's debatable. Really the right way to the technically correct way to write this would be C2H4O2. But I want to represent more than just the atoms in the molecule. I want to represent something about the structure, the function. So I put my hydrogen on the other side of those oxygens. That hydrogen is the one that's going to be donated in my acidic behavior. And so you notice when this breaks apart, I'm going to have that H plus aqueous. You could write H3O plus, but that gets into a different definition of acid-base behavior. We're going to have plus Na plus. So sodium hydroxide, I already spoiled it, is going to be aqueous, right? Sodiums are always and OH minus. Aqueous. I didn't give myself enough space, so I'll just do this. Sodium acetate, aqueous. I look at the bonds in sodium acetate. I'm going to go ahead and get Na plus, aqueous plus CH3COO minus, aqueous. And then H2O liquid. Don't break the covalent bonds. Don't break up liquids.
You only break apart aqueous?
Yeah. Yeah. So the way to think about it is we break up ionic solids dependent on the solubility rules. And that's kind of it, right? Aqueous compounds break the ionic bonds dependent on solubility rules. Yeah.
Shouldn't that be C2H3COO?
So actually, if I wanted to write it the same way as this, I just got carried away with the way I like to write it. But to be consistent with the problem, let's go ahead and just write this as C2H3O2 minus, so we're consistent. Just muscle memory. Acetic acid, CH3COO. Things that are identical on both sides. Right, pretty much anytime, and then now we can pretty obviously tell what type of reaction is this.
Acid base.
So, a lot of the acid-base reactions, pretty much all the acid-base reactions we're going to do in this class,
They're gonna end up like
will simplify down to this kind of, this like typical acid-base equilibria. Now, we are going to, oh, none of you have to take the 126, right? Okay, well, the place where this gets a little bit more complicated, where this is less true, is when you start dealing with equilibria. You notice in this problem, I assumed that the acetic acid completely broke apart, just like our strong acids,
you can't.
but it's not a strong acid. This thing is going to have some equilibria phenomena that we're not taking into account this quarter. But we'll talk about it some in 125. Other pressing questions? Yeah.
Can a reaction be acid base and redox?
Yeah. Actually, it can. So we create these categories. Remember, just like the way that I say, if it's soluble or insoluble, it's kind of a lie. The idea that it only has to be one thing is kind of like, well, not really, right? You can have something that is an acid-base reaction and a precipitation reaction. You can have something that's, I'm trying to think of acid-base and redox. That's a little less common, but I'm willing to bet it could. In the world of chemistry, I'm sure that it happens someplace.
I thought I saw it on the lab twice. The one that we're turning in today. Is it
Yeah.
likely that I didn't because it's not as common?
It might be that it's a redox reaction that you thought was acid-base, but it's actually just redox. What's the
Okay.
reaction you're looking at?
I have the net ionic. It's zinc solid plus 2H aqueous makes zinc aqueous plus H2 gas.
Ooh. So what made you think it would be acid-base?
Because I saw something where it was like a metal plus an acid makes hydrogen gas like an acid.
Well, so you're reacting with an acid, but you're not really. Depending on how you define base, that's not really an acid-base reaction. That's more of a redox reaction because you're going from H plus to H2 gas. So that's more technically a redox reaction.
Okay.
But in reality, which we're not going to get to this reality ourselves in this class, but in reality, you can pretty much look at any redox reaction as an acid-base reaction, or any acid-base reaction as a redox reaction. If you go to a different definitions of acids and bases, this is my 129 students do this to some degree. Well, there's a definition of acids and bases that instead of looking at this like idea of like, oh, you produce H plus, you produce OH minus, which is like surface layer, barely understanding acid-base chemistry, but does good as long as you're just dealing with strong acids and strong bases. When you go to the deeper levels of understanding, you look at acid-base behavior in terms of electron donors and electron acceptors, which starts to look a lot like redox reactions.
Yeah.
And it turns out they're almost the same thing. But not in this class. We're not going to do that.
Is this quiz 1 through 9 or
1 through 9.
1 through 10? Okay.
1 through 9.
I just look at 10.
If there are no more questions on the homework, any lab questions we should do before I turn off the video?
Oh, sorry, I have
Yeah.
one more.
Yeah.
The last one where it was, I don't have the net ionic written down, sorry, but is it just because nothing happened?
There's no reaction.
No reaction.
There's no net ionic to write down because
Yeah.
no reaction occurs.
So it's like nothing for the net ionic, nothing for the type, and then nothing for
Yeah,
observation.
just write
Just write no reaction, no reaction, no reaction.
Okay.
No,
Cool. I'm going to go ahead and stop this
Okay.
and upload it.